In this mini lecture, I would like to talk to you a little bit about an issue that comes up quite a bit in this course and future courses that you'll take in the sciences, and that's powers of 10. You may be very familiar with powers of 10 and how to deal with them from math classes or other science courses, and if you are, then feel free to brush through this without too much issue. But if you don't have a lot of experience in dealing with powers of 10, this might be a little bit helpful for you. Of course, there are many YouTube videos on powers of 10, lots of lectures out there for you, and don't feel free to look for any kind of lectures that can help you on this material. There's not a lot written in the textbook on powers of 10. It's sort of assumed that you know how to do this, and that's probably the same with the ALEX. So let me go over just a few pointers in terms of dealing with powers of 10. The issue that we're dealing with here is if you look at these two pictures here, the one on the left is just a little artist's conception of an atom. As I said in an earlier lecture, we can't see atoms, but this might be one way of kind of drawing a pretty little picture of an atom. And the question is, how large is an atom? And the answer is, in meters, it's a very, very small number. So for example, if we consider that a meter is around a yard, around 3 feet, 39 inches or so, then one atom in meters would be something like 0.000000000, anywhere from another 0 with a 5 to 1. So that's a pretty small number, right? And in fact, if then you start talking about, well, wait a minute, what's the mass of an atom? Well, we'll talk more about that in the next chapter. That's actually an issue that comes up in chapter 2 and in chapter 3. It's one of the primary topics of this course, is that in the units of grams, and if you think about it in terms of medicine, grams are used in terms of medicine. So for example, a piece of ibuprofen, Advil, might be zero point 0.2 grams. A Tylenol might be zero point 0.6 grams. So around a gram in that order of magnitude. The mass of an atom is 0.000000000000000. I'm going to keep going. It's actually pretty small. So these are really, really small numbers that we deal with in terms of atoms. But what about the really large numbers? The really large numbers would be considering, for example, a galaxy. You know, our Milky Way, that's our galaxy, that's the one that our star is in and our solar system is believed to have around 100 billion stars. Okay, that's a pretty big number right there. And if then we use all of the tools available to astronomers, they have determined that our star, which is out somewhere in one of the spiral arms of our galaxy, is part of a universe that has probably around 100 billion galaxies. Okay. So if you take a look, the number of stars in one galaxy will approximate that as 100 billion. The number of galaxies in the universe, another 100 billion. So if you ask, well, how many stars are in the universe? You would just multiply those two numbers together. 100 billion. So there's 100 million. 100 billion times another 100 billion. And that would be the total number of stars in the universe. Well, that is, my friend, a very large number, right? That's a huge number. And so doing arithmetic by using this notation, which we use throughout our lives, it's called decimal notation, where we count powers of 10 by putting zeros at the end of the 1. That is not a notation that works very well in the physical sciences, at least in many cases. So one way to deal with that is through prefixes, but another way is through using something called scientific notation, and that uses a type of exponential notation to deal with powers of 10. So what I'm going to do is I'm going to get rid of this discussion of stars and atoms, and we'll come back to atoms at least later. Oops, here we go. Let's go ahead and eliminate all of this. Okay, and let's go ahead then and take a look at how we deal with powers of 10 using exponential notation. Let me just get a little bit more of this out of the way. There we go. Okay, so now we have a little bit of room to work with. So the issue here is powers of 10. So this is the notation that we use. Essentially what we do is we say that if you have the number 10, we write that as 10 to the 1. And if you have 10 times 10, which we think of that as 100, we write that as 10 to the 2. And if you have 10 times 10 times 10, which in decimal notation would be 1,000, we write that as 10 to the 3. Okay? So 10 to the 1 is 10, 10 to the 2 is 100, and 10 to the 3 is 1,000. So suppose we have 100,000, just to show you a number here. Well, what you would do is you would put the decimal point here, go 1, 2, 3, 4, 5, till you get to 1. And that took 5, so we would write that as 10 to the 5. Let's say we have an even bigger number. Okay, let's go ahead and put in that big number, the number of stars in our galaxy, the Milky Way. Okay, that's 100 billion, right? So what you do is you take the decimal point, put it after the last zero, and just count how many spaces you have to go over until you get to the 1. So it looked like I had to go 3, 6, 9, 10. So there's 9, 10, 11. Looks like we had to go 11 times. So that'd be 10 to the 11. Okay? And that's essentially the idea. So now we can represent a really large number, like 100 billion, much more easily as 10 to the 11. Now, we can also do the same thing with small numbers. Okay? So let's take a look at the pattern here. 100 billion is 10 to the 11. 100,000 is 10 to the 5. 1,000 is 10 to the 3. 100 is 10 to the 2. And 10 is 10 to the 1. So continuing with this notation, 10 is 10 to the 1. 1 is defined as 10 to the 0. So we'll just have, if we have just the number 1, we would write that as 10 to the 0. Now, it doesn't normally make sense to do that because 10 to the 0, it takes up more space and it's harder to say than just to say 1. But we need that just to continue through this pattern. So now what we do is we ask the question, well, what if we have 1 over 10? Well, according to this notation, what we would do is we would say 1 over 10 is 0.1. Essentially what we've done is we've taken 1 and we've divided it by 10. So we're going to write that as 10 to the minus 1. So when you see a negative exponent, what that's telling you is that the number is less than 1. So 1 over 10, or 0.1, is 10 to the minus 1. 1 over 100 would be 0.01, of course, which is 10 to the minus 2. Take a look at the pattern, right? Every time you add a 0 after the decimal point, the exponent goes down by 1. So let's go one more. If we had 1 over 1,000, that would be 0.001. Well, that's going to be 10 to the minus 3. So there we're getting smaller and smaller by putting more and more negative numbers in that exponent. It's a really nice notation. It makes our calculations a lot easier. So now let me come over here. I'm going to, again, let's erase some of this here just so we have space to work. Okay, there we go. Let's do a little bit more here. This eraser here. Goodbye. There we go. Okay. So let's take a small number here, and let's try to figure out what the exponent is. Okay. So it's essentially the same idea as we did before. Remember how we just counted the number of spaces until you got to 1? We're going to do the same thing here. The decimal point started off here, so we're going to go 1, 2, 3, 4, 5, 6, and to get to the 1 we had to go here, 7. So until we get the decimal point to the right of that 1, we had to go 7 spaces. So that would be 10 to the minus, if it's less than 1, it's a minus, and then 7. Okay? There's an old acronym, a mnemonic, I guess you call it, for people to remember, and that is that left is positive. And of course, then what we would say is that the opposite of that would be right is negative. So right is negative. So you can remember it as lip. Meaning that if you're moving the decimal point to the right, it's going to be negative. If you're moving it to the left, it's going to be positive. So, for example, let's come back to 10,000. The decimal point's right here. We're moving it to the left. So if you're moving it to the left, I had to move it 4 spaces. That would be plus 4. And it is actually okay to write plus 4. There's nothing wrong with that. Or we can just write it as 10 to the 4. If there's no sign written, it's assumed to be positive. Of course, if it is negative, you're going to write the negative sign there. Okay? So that's one aspect of it. Again, I'm going to go ahead and erase all of this so that we can now move on into the issue of multiplying and division and dividing. So multiplying and dividing. Powers of 10. Okay. Again, you may have done this before, so if you're familiar with this and it's not an issue, just throw it away. You don't have to worry about it. But if you need practice in this, let's go through this issue. So when we multiply numbers together, so let's say that we're going to multiply 500 times 500. Well, there's several ways to show that. What we could do is we could say, look, this is equal to 5 times 100. Right, 500 is 5 times 100, times 5 times 100, because there's the other 500. And then we could sort of pick and choose what we want to multiply. 5 times 5 is 25, and then 100 times 100 is, well, 10 times 10, 10 times 10, so that's 10,000, right? So times 10,000. And then 25 times 10 is 250, and then you got your 1,000. Okay, so that's just one way to do it. 250,000 would be your answer. But suppose we wanted to do it a slightly different way. Let's come back over here and get rid of doing it this way. Okay, so here's how I'm going to do it. I'm going to say that we've got a number, 500 times 500, and I'm going to put each of these into our scientific notation, our exponential notation. Now, we don't have ones in front, we have fives, but that's a decimal number. So what I'm going to do is I'm going to say, okay, let's put the decimal points right there. And I'm going to go over here, 1 and 2. And I'm going to write this as 5 times 10 to the 2, right? So that would be our exponential or scientific notation. 5 times 10 to the 2 is the same as 500. Well, same thing over here, right? Decimal points here, move it over 2 spaces, so 5 times 10 to the 2. Now, here's what's nice. When we're doing multiplication, powers of 10, we can just add the exponents. That's a really nice aspect of this. It's actually one of the reasons that this type of notation was invented. So if I'm taking 10 to the 2 and I'm multiplying it by 10 to the 2, you just add the exponents. 10 to the 2 plus 2. So that's 10 to the 4, right? So now what you can do in this particular problem is you can pick and choose again. I'm just going to multiply 5 times 5. So that's 25. And then I'm going to take note that 10 to the 2 times 10 to the 2 is 2 plus 2, 10 to the 4. And I've got my answer here, 25 times 10 to the 4. And that's an exponential notation, and that's the correct answer. That's actually the same answer, 250,000, that we got using the previous method. Now, for numbers like 500 times 500, this type of notation is not really all that necessary. It doesn't save you that much space and time. However, it really helps out when you're dealing with very, very large or very, very small numbers. So what I'm going to do is I'm going to take two big numbers. I'm going to take 1.0 times 10 to the negative 16, and I'm going to multiply it by 3.0 times 10 to the plus 14. Again, you don't have to put the plus there, but I'm going to do it just for our purposes. Now, if we had to do this calculation using decimal notation, 0.0000 with 15 zeros, and then you have the 1, and then 30000 with 14 zeros, that would be a mess. So here's what we do. We separate this into two separate calculations. You take the decimal numbers and multiply them. I made these numbers easy. 1.0 times 3.0 is 3.0, right? And then you do the powers of 10 separately, and you add the exponents. Well, so times 10. Now let's add the exponents. Minus 16 plus 14 is minus 2, so 10 to the minus 2. And that would be our answer, 3.0 times 10 to the minus 2. That's pretty cool, right? That's relatively simple. Now, let me make this a little bit longer. Let's try another one. Suppose I'm going to do let's make it 1.5 times 10 to the minus 23. And I'm going to multiply that by 3.0 times 10 to the minus 16. Okay? Again, you have these really crazy numbers, 10 to the minus 23, 10 to the minus 16, but again, in the sciences, those are not crazy numbers. Those are numbers that you might see in a calculation because we are trying to measure things like the sizes of atoms, masses of atoms and molecules. So these are really small numbers. Again, same idea. You take the decimal numbers and you multiply them. So 3 times 1.5 is 4.5. And then you do the powers of 10. So now 10 to the minus 23 times 10 to the minus 16, you just add the exponents. So 10 to the minus 23 plus a minus 16. Remember, when you're adding negative numbers together, you just add them like they were positive and then put a negative in front of it. So this would be 10 to the minus 39 because negative 23 plus negative 16 is negative 39. So there's our answer. 4.5 times 10 to the minus 39 would be our answer. Not too bad, not too shabby, right? That's a pretty powerful technique that we can use. The other issue that comes up is what if you're doing division? Now, again, I'm not going to go through proofs on all this stuff. That's something you can do in a math course, so you can look it up on your own. We are just going to use what's been proven to be true, which is the issue that if we do division with powers of 10, there's a simple methodology we can use for that as well. And so essentially the idea is this. Suppose I had 1 over 100. And we're going to call that 10 to the minus 2. Because remember, 1 over 10 is 10 to the minus 1. 1 over 100 is 10 to the minus 2. Suppose now I have a division problem. Suppose I have 5 times 10 to the 4 divided by 2 times 10 to the 3. Now, I'll show you just real quick what we could do. We could convert these numbers into decimal numbers, and this would be 50,000. and this would be 2,000. And if you recall back in arithmetic, they may have taught you that if you have zeros in a division problem, you can just cancel them, right? Really what you're doing when you're canceling them is you're dividing both the numerator and the denominator by 10 to make it smaller. Okay, so now you get 50 divided by 2, which is 25. So that calculation could be done that way. But here's essentially what you're doing is every time you have a 0 in the numerator and you have 1 in the denominator, you're essentially canceling them. You're subtracting them out of the powers of 10. So what we can do is we can say that if we have 10 to the x and we're dividing that by 10 to the y, the result of that calculation is 10 to the x minus y. You're just subtracting whatever the exponent is in the denominator from the exponent in the numerator. Okay, so let's try this problem that I've shown here that way. The decimals, it's not an issue, right? 5 divided by 2 is 2.5. We can do that easily. But what about the powers of 10? So times 10 to the 4 minus 3, right? 4 minus 3, because we're taking the exponent in the numerator and we're subtracting the exponent in the denominator. So for this calculation, 4 and 3. Well, 4 minus 3 is 1, so that's 10 to the 1. Remember we said 10 to the 1 is equal to 10? So our answer then is 2.5 times 10. Well, that's just 25. We get the same answer there. Again, using this idea of just subtracting the denominator exponent from the numerator is not a big deal when the numbers are small, like 4 and 3, but it really is an issue when you deal with all kinds of crazy, or what seemingly are crazy numbers. So let's make some space here. And try one here. Suppose we have 36 times 10 to the minus 19, and we're going to divide this by 6 times 10 to the minus 27. Okay. Well, we have a small number in the numerator and an even smaller number in the denominator. And if you recall, when you take a number and divide it by something that's smaller, you're going to get a number that's greater than 1. So our answer should be a relatively large number. So here's what I'm going to do. The decimal part is easy, 36 divided by 6, so that's 6. And then times 10, and then what we're going to do is x minus y, right? We're going to use the exponent up here, which is x, and the exponent which is down here, which is y. And so that would be 6 times 10. I made these numbers negative just to complicate things. Minus 19 minus 27, right? If you are subtracting a negative number, that's like adding a positive number. So this would be 6 times 10 to the minus 19 plus 27. Right? Minus and minus is plus. So now minus 19 plus 27, that would be plus 8, right? Because 27 minus 19 is 8. So 6 times 10 to the 8th, and there's our answer. Okay? So that one's not too bad. That, even though these numbers are really, really small, we get our answer. It's certainly greater than 1 there. That's about 600 million. That is 600 million. So if we wanted to put that into decimal notation, we'd have 600 million there. Okay? So I hope that this helps you if you've had, or if maybe you're just a little bit rusty on powers of 10. It's been a while since you've done it. Get in touch with me if you need any more assistance on this, and hopefully this will help you.